Hello everybody, my name is Glenn Shrest. I'm leading up the BlindMate ORv3 liquid cooling development. We're going to be doing a lightning talk where we're going to walk through the various work streams that we have. And I'm going to start off with an overview. And I'd ask if you could save your questions to the end so we can kind of flow through it, and we'll have some time at the end for questions. I'm a technical lead over at Meta, and Amanda Bryant from Danfoss couldn't make it today, but she was a big part of developing this slide deck as well as a big contributor to our group. So I'm going to talk a little bit about the makeup of our group. Our group includes liquid cooling component suppliers, solution providers, technical experts, ODMs, and end users. Our goal is to develop specifications and interfaces for BlindMate liquid cooling solutions to be used in OpenRack v3. This includes BlindMate specific frame interfaces and support brackets, manifolds, BlindMate valves, unique hose and tubing solutions, as well as IT gear concepts. I want to kind of be clear here, we're not developing a valve here, we're developing a holistic solution, so our scope is quite wide and complex, which makes all the partner work with all of our suppliers super critical. We've also published a few best practice white papers to help educate the community, and I'll talk briefly about those. Our work streams. The frame. We're developing interfaces, support brackets, and structural enhancements. I'm going to talk briefly about it a little bit later in this slide deck, but as we get further along in the discussions, we'll get more details from others in the group as they come up. We have the BlindMate Manifold work stream, which includes interfaces and design specifications. We have BlindMate Quick Connector as well. We're developing specs as well as developing components from multiple suppliers. And the BlindMate IT gear specification, which is, we're not making a spec where you have to make a chassis just like what we're going to be providing, but we're going to provide interface requirements as well as a design concept that people can leverage for their own designs as needed. And then on the hose and tubing solutions, there's unique requirements around BlindMate that we'll get into a little bit later, and we've been working quite a bit on that. And then on the white paper side, we have a manual couplings and hoses best practices that was released last year, end of summer, through COVID, which was pretty cool to see us actually make some solid progress despite those challenges. And this past summer, we released a logistics integration best practices, and I'll talk a little bit more about those moving forward here. So let's talk about basically the concept for ORv3 and how we're mounting manifolds. So this is a review of the rack. The manifolds are installed split on each corner of the rack with the cold and hot on opposite sides. And the idea is to maximize the amount of service space between the bus bar in the middle there and each of the manifolds for things like modules and fans. And then on the manifold side, the manifolds are going to feature what we call the socket side of the connections with the valves. So that's what those yellow geometry is showing there. On the IT gear side, there's going to be the plug side, which is those yellow items there and kind of shadowed inside the box. They're kind of in a protective area inside there, as well as unique features for mounting them and interfaces for BlindMate injectors and things along those lines that we'll talk about again a little bit later. And I'm being high level on purpose. I want to give people kind of an understanding before we dig down a bit more of the details. So stay tuned. And then on the frame side, we have interfaces for mounting the manifolds as well as structural enhancements to overcome things that we'll talk about in a minute here. And the features include stiffening members to counteract the mate forces from the fluid pressure, as well as the springs and all the valves. You start adding them all up, the forces add up very quickly. The manifold interfaces and mounting features will also be in the rack. I think Stephen talked about this a little bit earlier. The idea is they're going to be bolt-on items that you can add as needed. They're not fundamental to the frame to make your ability to change fairly easily from a regular rack to a BlindMate rack. We also have been using an extensive amount of FEA analysis to optimize this design. And we're talking about FEA by the manifold suppliers, by our folks at WeWin on the IT gear side, as well as Rital. We have a guy who's spent a tremendous amount of time optimizing the design in terms of a structural analysis, which has been awesome. Great teamwork there. And then we've had some challenges around the need for tighter tolerances with BlindMate. And when you're talking about a frame and you want to make a frame at scale, sometimes those manufacturing methods aren't exactly the most tight in terms of tolerance capability. And so there's been kind of this give and take in terms of optimizing around those trade-offs. We're also focusing on ease of assembly and modularity. And a little bit more on the manifolds here. Similar theme here you're seeing around tolerances is if you think about a manual connection with a hose connection, you really don't care about where those valves are because you have a flexible hose connecting between elements. Whereas in a blind mate, you really care about registration in terms of where it is. So there's a lot of work around that and getting that to work out. I can't tell you how many tolerance loops the team has done. We have registration features for ease of assembly, and over the last build we made, the early prototypes, we made a huge improvement there. Also, the manifold is actually a structural element. It has to help counteract these loads. It can't be this thin metal, thin wall design. It actually is a key part of ensuring the design is robust. And we're going to define the key interfaces and features, but we're going to allow freedom for suppliers to do things in non-critical areas. We're not going to specify every radius, every wall thickness, every detail. We're going to provide the interfaces and the features on the frame and key location requirements for the ports. We've also developed this past year the idea of a modular air purge option. So if you look in the upper right there, that kind of copper colored piece, it actually can be removed with a quick connector. So if it gets damaged, you don't have to throw the manifold away. You go get your replacement, you put it in, and you're still off and running. And then another thing is we're trying to keep it simple and consistent with the industry. So all of our port callouts are per industry standards. On the blind mate valves, due to all the rack tolerances, deflection discussions issues we talked about from the mate forces, gaps between gears and racks, all those tolerances that stack up, this design needed to be different from a standard solution that was readily out there. We have increased radial and angular float. We have a longer working range, which means the range in which the plug and socket can work, whether mated, and that's critical for things around tolerancing, handling, shock and vibration. We don't want things leaking, but you also want to have really good thermal performance despite those tolerances. You don't want to have a drop off and an impedance change during that working range. One of the key criteria early on that the team set off was we also didn't want, in a sense, for the valves to turn into guide pins, where you have the IT gear mating in and the valves basically holding everything in place. So part of the reason why there's such large floating capability is we wanted the gear to be able to move freely with respect to the rack and manifold so that we're not creating these loads and potentially creating damage and leaks, which is a goal we don't want to have. The other thing is interoperability between suppliers. It's actually been one of the biggest challenges in our group because we have 4 suppliers. They're all designing their stuff in their own way, but we want to make sure that we have reliable connections, excuse me, and no binding, no leaking. But we made some really good progress this last time, and we currently have 4 suppliers that are developing solutions. On the IT gear side, it varies from a standard IT gear in a few ways here for blind mate. The interfaces for the plugs themselves, there's unique features in there. We have hose guide features inside the gear to route the hosing and tubing to kind of address it so that we don't have issues with it fighting with the valves. And then we have lawn stroke injectors to provide mechanical advantage during install. Notice it doesn't say ejector, it's an injector. Its job is designed to overcome the mate forces from the fluids and valves and help the user install it into the rack. Hose and tubing. We've been developing, this is, I can't understate the amount of work that's here. It sounds like a simple topic, but it has not been. We developed hose and tubing solutions to meet the standard key criteria of mechanical, pressure, fluids, chemicals, material compatibility, those type of things. But the floating nature of our plug side requires us to be very careful in terms of how we deal with this area. The hoses we need to consider how it's being guided. We need to consider how it's terminated, as well as it needs to be flexible. We don't want it fighting our valves when they're trying to float and mate and align. So we developed some hose guide solutions for internal routing. We've done a lot of work on test methods and acceptance criteria for the hoses, and we've done an extensive amount of testing on multiple solutions. We have the whole idea, kind of summarizing this, is these are going to be reference options. We're going to list them as potential things you can use, but we're not requiring the end user to use these. It's like, we can give you a valve, okay, but now how do I use the valve? What do I connect it to? We wanted to kind of provide, like I said earlier, a holistic solution. So we're going to list these in the spec as options, and there'll be some information on those. And white papers. Last year we released this manual couplings and hoses best practice. It talks about coupling types, hoses and tubing construction, best practices, test methods, and regulatory standards to consider. It basically gives folks kind of a background on that area. And then most recently, this past summer, we spent quite a bit of time here. Nigel Gore from Vertiv was a big help here in heading up a lot of this work here. We developed the Logistics and Integration Best Practices white paper, focusing on areas such as testing, integration of gear, and shipping. And that was put out again in the summer. So kind of some high points in terms of what we've done over the past year. We completed our first level of valve testing at the component level as well as at the rack. We've done improvements in manufacturability of the manifolds. We've reduced significantly the user forces from inserting the IT gear into the manifolds due to fluid pressures and springs, as I mentioned before. We've made a big jump in terms of improvements in cold plate serviceability, and we're going to get into some of those things when we talk about the valves on the IT gear side. We've developed and tested new hose and tubing solutions. We've made some refinements to the hose routing. As I mentioned before, we did a lot of learning over this past year on the effect of the hose routing and design on the performance of the interfaces. We've started a lot more focus on interchangeability testing. We're going to be doing quite a bit of that moving forward in the next year as we ramp up our testing. The blind mate test specification requirements, whether it be on the manifold side or the valve side or the IT gear side, we've made quite a bit of development in terms of how the details in those areas as we're moving forward and learning. And then of course we published the integration and logistics white paper, excuse me. So I do want to say we do have over at the Meta booth, we have a rack with all the blind mate gear in it. And we also have a table with the IT gear. You can look down inside and see our cold plate loop. You can see the valves. When you have some time later, go take a look over there, and there'll be people there to ask your questions as well. Thank you. So Tim?
So hello, I'm Tim Marquis. I'm with Parker Hannafin, and I'm here to represent the valves and the quick coupling portion of this, as well as Noman from Meta. He's going to be talking a little bit more about some of the hose routing and some of the lessons that we've learned here. So really, some of the objectives of getting through this is just kind of show how, as a group, the different suppliers that we've been able to work together to improve the blind mate quick connectors and be able to integrate this into this ORv3 rack and power design. So, and then there's just a lot of overall performance parameters and design parameters that we've been able to develop jointly through several different iterations. Our overall design premise, as well as optimizing things for connection forces and flow impedance and flow performance, and making sure that the parts will always connect and center appropriately as we go forward. It's moving too far for me. Okay. Yeah, I'm just one of the part of the team. It has been a collaboration of several different members. Unfortunately, not everybody could be here today, but it was, I think the names keep changing, but the people have been all the same. So our design premise, the initial testing that Glenn talked about, it did provide a decent amount of insight into several areas that we wanted to address. As we talked about, a lot of those manufacturing tolerances for the racks, we tried to get a lot more tolerance within the blind mate valve itself compared to maybe what the industry has traditionally done. And to do that within this design performance, each vendor, we've standardized the general interface, but there were some things that we decided as we continue to go further to help standardize a little bit further, to help with that interface and with that learning as we continued through the first couple rounds of our prototypes. There was a few dimensions we had to add, mostly around interoperability and connection, and then we had to agree on those and kind of bring those back to a standard. So as Glenn said, one of the hardest parts is working together as a group of different companies to kind of agree what makes sense. In terms of connection forces and springs, one of the main areas to try to get to, obviously getting the latch mechanism to connect everything together was something that was key, and trying to minimize the amount of connection force that we had on each blind mate connection, because there is a large number of these per manifold, and then you try to connect several together all at one time, it does add up pretty quickly. So then the spring force was optimized to make sure that it would overcome any kind of O-ring friction, but still be able to close all the valving, but also allow for proper flow. The spring material and design, the properties, we worked out the appropriate stiffnesses to be able to make that work for each size. And then we did test iterations for the mating forces and then working on improvements for that. Because it does have a high impact on the ergonomics that you see right at the end when you get into the latch mechanism. You know, because that separation force is made up of several different elements as you go together. That you got your spring forces, you got hydraulic separation forces, any kind of hydraulic pressure within these couplings as you put them together, and any kind of friction that has to be overcome as you keep going. Another key area that we had to work through was flow performance. Trying to make sure consistent flow performance through each valve was important to us. Not just consistent from the interoperability standpoint, but also depending on how much axial tolerance you have between when you're start to be connected or when you're at a maximum connection condition, and try to maintain not just the flow impedance of the interchangeability, but all those different in-case conditions that it comes into a fairly narrow band. Thankfully, the team was able to work through, you know, I think everybody came in below our initial requirements, but we were actually able to optimize and bring everybody in a fairly narrow band as we went through. So that was actually a pretty nice collaboration with the team there. In addition, as Glenn mentioned, we found that there are many different factors that can influence how these couplings work, and the hose conditions was a big one. You know, where the clamp design is, how much force there is, you know, any kind of any kind of loading on that backside really caused things to change as we went forward. So trying to maintain a consistency with that part was important, and then having the testing of this within a standardized set of parameters was really key. As well as there was several things we did with the male part to ensure that the part of the to ensure that it had it was be able to be installed with a panel nut on the backside instead of being able to have something that's a little bit more difficult to install. I know, Noman, you wanted to go through the rest?
Thanks, Tim. All right, my name is Noman Mithani. I'm a mechanical engineer at Meta. And the next part of this is really flowing into what Tim just talked about, how important hoses and tubing is to the operation of this blind mate quick connector. So why is it important? It's hoses and tubing is the interface between the blind mate valves and IT gear. So this presentation is going to cover a couple of choices that we went through in terms of materials. The hose barb interface that is the connection between the hoses and the IT gear barbs. A bunch of the testing procedures that were spanned over the last year and a half that validated the hoses and tubing that we picked, and then also a lot of the hose routing and chassis routing that went into making sure that the blind mate quick connectors are centered and operate as we want. And then some new products that were developed along the course of this that are specifically meant for IT gear. This has been a collaborative effort that included, our partners at Fluid Conveyance Components like Danfoss and Parker, as well as system integrators that are putting these systems together, materials and coolant specialists, existing liquid cooling vendors, some of them that are showcasing in the expo hall today, and then as well as data center end users, so especially at Meta or other companies, other hyperscalers that are already putting out these products at scale. So the two main choices that we decided for in terms of material are rubber and plastic. So before I get into that, one difference between hoses and tubing, is that hoses are generally flexible materials that are stacked in multiple layers with reinforcement in between. Tubing, on the other hand, is a single wall construction, and it's usually stiffer to maintain the same kind of performance and pressures that we're looking for. But it needs some kind of special geometry to make them flexible for our use case. So on the rubber side, we picked EPDM. The main advantages there is that it's proven fluid compatibility. It's already being used widely in industry today. And because of that, it's very mass manufactured and it's cost effective. It's also used in a lot of other industries like hydraulics and heavy industries. So it's been proven out. Because it's rubber, it's also flexible, but at the cost of larger diameters. Because it needs multiple layers with reinforcements in between, it's generally going to be a bigger diameter than something that's a single wall. It also creates an elastomeric seal at the barb interface. So that's really important when you're installing the hose into our blind mate quick connectors or the manifolds. It needs to be easy to install, but also create that clamping force that's needed to hold that seal. On the plastic side, we picked PTFE. That's a fluoropolymer, similar material to Teflon, for example. And because we picked a convoluted geometry, and what that means, it's a spiral, it's able to be very flexible and it has a very tight bend radius. It's also naturally very chemically inert and flame resistant. And then just some other add-ons that are, I guess, freebies are it's translucent, so that aids in servicing and operation, and has very high dielectric strength. So the hose barb design is the interface between what's on the valve and the hose inserting into it. So the main requirements there were we wanted a clamp-free design to aid assembly and efficiency of rework. And what that means is we don't want any screw clamps adding on top of the hose barb seal. And then while through all of this, we want to hold 5 times working pressure consistently over long periods of time and elevated temperatures. And just the high reliability standards that we have for hyperscalers at scale. And then as well as staying within the dimensional requirements of the blind mate plug. So the 2 main iterations between EPDM and PTFE were a little bit different. EPDM is already conventionally used with a push-on style without clamps. So that was generally adopted from existing designs. PTFE is a little bit different because it hasn't been done as much in practice. And what we're trying to juggle here, balance here, is that we want to lower insertion force for ease of assembly, but still have enough clamping force to maintain the seal and the pressures that we're looking for. A couple iterations on the hose barb design for PTFE. It has the same requirements of a clamp-free design, but something new that's added is that we want installation without buckling the tube. It's a single wall, and it's thin single wall, so it has a tendency to buckle if you're inserting it with a very high mate force. But we do want enough clamping force that we're not degrading the seal of it over its lifetime. So what we did is we started with a standard DIN barb geometry and modified it from there through the testing we conducted, which I'll get into in the next slide. There was a couple geometry iterations going from a 3-barb fitting to a 2-barb, and just optimizations into the diameter to get it right where we want it to be. So some of that testing, what we did was we worked with all of these industry partners to define a set of requirements that meets the performance and reliability requirements that we have, and then set out a long list of tests and validations that we conducted with our partners at Parker and Danfoss. The main ones here are really just hydrostatic pressure, temperature, creep resistance, accelerated life test, and then some of the smaller ones that actually become pretty important when you're using these for long periods of time is permeation. So how much coolant is being lost to evaporation over time, fluid purity, so what kind of chemical interaction these hoses impart on the coolant. That has a huge impact on the life cycle of this cooling solution. So here's some pictures of both at Meta and at our partners of testing that we conducted over the last year and a half to validate the few products that we've outlined in the next few slides. And this is not an exhaustive list of products. So like Glenn mentioned, this is more of a guideline of if these requirements are met, then we're trying to make sure that it works with the rest of the solution. So like Tim mentioned, chassis routing is a pretty important part that we found out. We know that what our systems are going to look like in the future. We know upcoming industry trends for high thermal load IT gear, so if that's AI, ML, or other HPC workloads. So we can take that general board design and then map that out to where the blind mate quick connectors are going to be, and then see where does the hose routing need to be, what kind of flexibility does it need to have to aid valve centering, and then as well as in lower insertion forces. So that's where flexibility, bend radii, hose guide location, and length have a pretty massive impact on this valve centering and insertion force. And then over the last year, we've tested extensively on hose routing parameters to aid all of these. And if you look at the meta booth, then you can see an example of a blind mate chassis that has this specific orientation that we're still optimizing, but it's something that we feel is indicative of a future IT gear chassis. A couple of the products that we've verified over this testing is a new Danfoss EPDM hose that is specifically more flexible for IT gear applications, as well as a Parker EPDM hose that's existing product that has the same flexible EPDM tube and cover with a textile reinforcement in the middle. We also worked with Parker to create a new PTFE convoluted tube, and these are existing products, but they have to be optimized for our specific use case. So the convolution pitch, for example, to aid flexibility, but getting the right balance between flexibility and flow impedance has been really important, as well as the wall thickness for the balance between strength in terms of pressure and temperature holding, and as well as elasticity for getting it installed on the barb. So this is a non-exhaustive list of all of the development partners for both the blind mate quick connectors as well as the hoses and tubing that we worked with. And I think we have Daryl next to talk about blind mate manifold.
Thanks, Naman. Good morning, everyone. Thanks for joining us here. So my name is Daryl Daniel. I'm a mechanical engineer with Meta on the infrastructure team. And in a little bit, I'll be joined by my colleague, Scott Stammer, who's the engineering project lead from Invent. Today, we're going to be talking about some of the development updates for the blind mate manifolds. This is a collaborative effort, and this is a few of the companies that work together on these development efforts. So what is the blind mate manifold? Simply put, it's a hardware interface between the IT gear that's in the rack and your coolant distribution source, whether that's an in-rack remote pumping unit or like facility fluid coming in from the plumbing above your rack. When we started, we had a set of goals. We wanted to minimize the service impact or downtime during maintenance. We also wanted to minimize the impact to the rear FRU access of the IT gear. You may still, sorry, I'm going to take this off. You may still have, traditional air-cooled equipment with those systems, and so you still need rear FRU access for things like fan modules. We wanted it to fit a standard OpenRack V3 via hardware add-ons. So, as Glenn and some of the other team members mentioned before, we don't want to burden the cost of a standard ORv3 rack with liquid cooling features if you don't need them. So it would essentially be a bolt-on kit, a set of brackets that you add. We wanted to define some common interfaces for mounting the manifold to the rack, but we don't want to be overly specific in terms of how those manifolds are manufactured. We want to allow flexibility for the vendors to innovate and create their own designs. Using industry standard port geometry was very important for us. And then, of course, we wanted to promote uniform coolant distribution throughout all the circuits within the cooling loops. So that it's predictable and you understand the thermal implications. At a high level, for those who aren't familiar, On the left, we've got an ORv3 rack. This is a rear view, and you can see we've got two blind mate manifolds mounted to the rear. We've got a hot side and a cold side. In this implementation, you can see some of the hoses coming out of the bottom. One of those would go to your heat exchanger. The other would be coming from your coolant distribution source. However, the spec is going to be flexible in that if you have facility water coming from the overhead plumbing, you could actually remove the air vent that's at the top of the manifold and replace that with a barb geometry that you could then bring hosing in from the top. So we intend to make the spec flexible in that regard. If we take a look at the right, this is one of the manifolds, kind of an overview of some of the components on it. We've got the tube itself. And you'll notice the 3 red boxes. Those are going to be our rack interface locations. There's an upper, a lower, and a mid-rack interface. So we'll be defining the geometry around that within the spec. Then, of course, we have the actual QC sockets themselves. And then, again, in this particular implementation, we have an air vent at the top. But, again, that's flexible, and you could change that to a barb if needed. So as a team, there's quite a few tolerance challenges that we faced as we started working through the development. We have tight positional tolerance requirements for the quick connects themselves, and that's largely driven by the overall system level tolerances. If you think about it, we have a rack, we've got the IT gear that goes in it, we've got the manifolds, and then all the components as well. And speaking of the rack, there's some fairly large rack level tolerances, which are due to some of the manufacturing processes for the sheet metal in the rack itself that are a major contributing factor in those tolerance loops. The raw tube, the stainless steel tubing that's used for the manifolds, have some inherent large tolerances built into them, and that can be in the form of bowing or twists in the received raw tube stock. So that has to be addressed from a manufacturing standpoint of the manifolds themselves. And then, of course, if you consider how the manifolds are mounted to the rack and the depth of the QCs themselves, any small angular skew on the manifold actually ends up having a fairly large displacement at the tip of those QCs, and so the design needed to accommodate that. Some of the design improvements that we made from previous iterations that were shared with the community is we made some improvements on the manufacturing designs of the manifolds for large-scale production, right? Keeping that in mind that is the end goal is to scale these up. We also are making sure to use common hardware at both the upper and lower rack interfaces. And along with that, we improved some of the accessibility of that hardware versus previous manifold designs, where some of the fasteners were blind, had blind installation, and you couldn't really see as you were installing them. So in the new designs, you have full access and visibility to the fasteners while also maintaining access to the leveling feet at the bottom of the rack. We also added a mid-rack interface versus the previous designs of the manifold, and this really helps us better control the tolerances in the front to back direction for the manifolds, and it also provides a structural stiffness to both the rack and the manifold as those are tied together now. So another change that we made is we pulled the air vent in line with the tube itself. In previous iterations, that air vent was actually offset into the hot aisle, and the protective sheet metal pieces that protect that air vent were also in the hot aisle. So those are now in line, and which means the total solution is fully within the envelope of the rack now. So now I'm going to hand it over to Scott. He's going to walk you through some of the simulation and testing efforts that we've gone through during this development effort.
Thanks, Darrell. So throughout the development, multiple suppliers did FEA simulations at various levels of integration. And this was done to ensure that the structural requirements were met to give us the tolerances that we needed while still maintaining the strict geometry limitations that we had essentially self-inflicted because we wanted to maintain that design flexibility that we've been talking about. We want to be able to have as much open area as possible for various options. So we ensured that the QCs maintain that within the prescribed tolerance zones, as we mentioned, as they open up, they can actually decrease the flow through the system. And if it opens up far enough, if there's enough deflection within the manifold, you can actually stop fluid flow completely versus just reducing the fluid flow. So flow distribution, why do we care about that? There's manufacturers that affect that. The QC variation between suppliers, as much as we try to make them consistent, there's always going to be some variation between them. The passive cold plate loop within the IT gear loop, that is always going to have some variation as well. And even the manifolds themselves, even within one manufacturer, there can be some variations. All those will stack up to create potentially some different restrictions in the system. So what we found was that as the coolant flow variation increases within the rack, the case temperature differences also increase. So that then requires additional coolant flow to the rack in order to meet the thermal goals amongst all the chassis. The problem with that is that results in a lower coolant return temperature, which you then need a higher fan power in order to reduce that approach temperature. So to combat that, the general goal is for the flow distribution to be within 5% of all the branches. So flow simulations have been conducted to characterize the flow distribution across the manifold and identify possible design improvements. What we found was that higher branch circuit impedance results in a more uniform flow distribution across the rack. Also, minimum required branch circuit impedance decreases as the flow rate decreases. So we actually did some real-world empirical testing. We simulated the chassis loops with a modulating valve so that we can adjust the flow rate and the restriction through that. We installed flow meters, temperature sensors, and pressure sensors in the dummy chassis to monitor the flow conditions. And we used a coolant distribution unit, or a CDU, as a way to provide the various flow rates that we needed for the various testing. So the various member companies collaborated together to share insights on various manufacturing techniques for the manifolds. As Daryl mentioned, there's a lot of variation in the raw material that comes in, and then the manufacturing process can really add a lot to that. So we worked together to share insights on what worked, what didn't work, and how we can make this better to be able to meet the spec that we need, as well as develop the spec to make sure that it's actually going to be manufacturable at scale at a reasonable cost point. We can make anything tight tolerance, but that doesn't mean we can actually make it at a point that it's going to be a valid solution. So the teams really worked well together to share that knowledge and make sure that we have a solution that's viable. Part of that was adjusting the tolerances on the spec itself for the manifold, and we wanted to make sure that we were taking into account the various manufacturing techniques at the companies, as well as, again, that raw material, but really meeting the system level tolerance requirements. And then we also shared the flow simulation and FEA results with the OPCP workstream to identify and discuss areas for improvement. Next steps, testing is in process right now for the round 2 manifolds, as well as the QC designs from all the different partners. We mentioned that it is in the booth right now, so you can see that on the floor here. But we're actually getting some data to be able to say how accurate our testing results were, or our simulation results. And then based on that, we will be updating if needed and finalizing the spec for the manifolds so that we can make another round and then start to develop the standard for the rack interface as well as the blind mate manifold itself. And as Daryl mentioned, there is a alignment feature that mounts separately to the rack. That is getting some updates. That we found that was a feature that really is contributing a lot to the tolerance stack up. So we're making some adjustments to that with the rack manufacturer. Once that's done, we'll be able to release that as well. And I'll turn it over to.
Okay, thank you. Yeah. Hello, everyone. Hello, everyone. I'm Pico from Win-Win. I would like to, in the following 10 minutes, I would like to introduce you the ORv3 brand mat liquid cooling IT gear. There are 3 major contributors Chen Yu Xu from the Meta, Chris Lee and I from the Win-Win. There's four sections. I will introduce the IT gear design requirement and the IT gear overview. Chen Yu will introduce the BMQC module design concept and injector design concept. This POC design is based on the ORv3 requirement and it's high the 3 OU. There is a 40 volt power clip to provide power, and a QCs provide a liquid inlet and outlet. Also, we have the injector handles and the release module to provide the installation easy and efficient. For the section 2 IT gear overview, just to give you a hands up, this is a TTV simulator GPU chassis, not necessarily a product. On the front side, we have a 2 injector and a release button, a TTV module and system manifold in the chassis. 4 BMQC plug on the rear side to provide 2 for liquid inlet and 2 for liquid outlet. We also have a hose guide to concentrate the hose movement while installation, and 4 fans to cool other heating components in the chassis. Hi, Chen.
Thanks, Pico. My name is Chen Yuxu. I'm a mechanical engineer from Meta. So today I'm going to cover the BMQC module design concept as well as the injector design concept. So the BMQC module, this is an important piece of the blind-made liquid cooling chassis. So it is located at the rear of the chassis. The left picture shows our old design. Essentially, we use a retainer ring to mount the BMQC plug onto a mounting bracket, and then drop the entire thing into the chassis. So for this design, we found that the retainer ring is very challenging to install and remove. So and also on top of it, it also couples to BMQC together, which is not that great for serviceability. To address that, we made some design changes to improve the BMQC module design for better serviceability and DFA design for assembly. So on the right, instead of using a retainer ring, we change it to a lock nut, and then use a socket and torque wrench to mount the BMQC plug onto the chassis. So this design is more modular, meaning that whenever there is anything failed, we can simply swap out the components without touching the other BMQC or the other liquid cooling loop. So we have also run some FEA simulation to make sure that the design is robust enough. So this is to ensure that there's no large deformation on the chassis because the loading force from the BMQC is pretty large. So making sure that we don't run into issues. The simulation result shows that the deformation is very minimal, and the result is acceptable. So to the injector design concept, so we have 2 pairs of the injector on the front of the chassis, which provides a long stroke and mechanical advantage to install the IT gear chassis into the rack. So when we designed this injector, one challenges that we run into is the long stroke, because the the QC has a very long stroke, and for a typical injector with one pivot point, the stroke is not simply not sufficient. So we came up with this injector with exceptional long stroke to cover the QC mating stroke. So this animation shows basically the stroke for the QC mating as well as the injector. So essentially, this is the process when we install the IT gear chassis into the rack. Mechanical advantage is another milestone when we design an injector. So when we install the IT gear chassis into the rack, we have several forces to overcome. One is the QC spring force from the QCs due to the fluid pressure and the spring force. And we also have the bus bar mating force coming from the rack bus bar. We also have the insertion friction between the IT gear chassis as well as the rack rail. So to install the IT gear chassis into the rack, the install force needs to overcome the sum of all these three forces, which is large. But with the mechanical advantage of this injector, we are able to bring the install force down about 80% to make the system installation easy. Quickly walking through some of the other functionality of this injector. One is the lock function. Basically, it retain the chassis within the rack, and also the brake function. So we have this release mechanism between two injectors. That is, so when the user press the release button, the injector retainer on the sides are going to retract and release the injector. So when the IT gear chassis is installed in the rack, there's always forces coming from the BMQC on the rail. So due to the fluid pressure and the spring force. So after the user press this release button, because of the force is always trying to push the chassis forward, it might also pop out the injector, which might be a safety hazard for the users. So we also designed this brake function into the injector, so to prevent this scenario from happening. So essentially, it is a kind of a brake function on the injector. So after the release button is pressed, the injector handle will not pop out immediately. So within the design, we use a spring to provide this brake function. With that, that's all our presentation for the blind mate IT gear chassis. Open to questions.
Is there any kind of a design benchmark for loss recommended for, considering different IT gears, like a compute node, GPU node, because the flow rate needed for different gears should be different, or less just a reference design so far?
Can you repeat that? I couldn't quite hear that. Sorry.
For the recommended for, so what is the design guideline for the cooling capacity it can support? Is this only focused on the compute node, or it can be a different IT gears? Because the cooling capacity, is kind of not to mention in the presentation slides.
Yes, we're working towards certain flow requirements, and flow distribution within the rack is not tied to a particular architecture. It's to particular flow levels. And once we have more detail on what that's going to be, and we kind of are comfortable sharing that we can meet those numbers, we'll share those.
So that including the number of stations it can support. So far, it's also not finalized yet, maybe.
You mean as far as number of ports?
Yes.
That's going to be up to you, right? Oh. We're not going to specify the number of valves. We're not going to specify where they have to be in particular. We're going to recommend some general guidance relative to, say, a datum in the bottom of the chassis for specific locations. We'll make recommendations, but the idea is this is very flexible for what you need.
But in the presentation, it has indicated the cold side, the supply side, has to be in the left side if we face in the rear.
Yes.
So that's a standard. That's defined already, right?
Yes, we're trying to keep that consistent, at least at high level. consistency.
Okay, all right, thank you.
Good questions. Thank you.
Have you guys considered degradation on either the hoses or tubes that you're talking about, either over life or based on interactions with the fluid or the ambient conditions, and how that may, how those mechanical and structural changes may impact the interconnects at the barbs and various fittings in the system, and therefore kind of defined what a maximum useful life is for these kinds of systems?
Yeah, that's a really good question. We are considering the effects of pressure and temperature over time, as well as the effects of the coolant has on the hose, especially the hose. It's not so much the tubing, especially with a PTFE tubing. It doesn't really leach any chemicals. It's pretty stable over a long period of time. But rubber does change over time. It can become brittle, and it can be porous. So what we're testing is at least a 5-year lifespan, and that's what we're trying to simulate with our accelerated life testing. And so that includes both mechanical flexibility as well as chemical compatibility. What does the coolant look like after it's been exposed to elevated temperatures over 5 years, for example? All of that has to meet our general requirements, and so that's what we've tried to validate the products with.
Are there any problems if we install security doors on the rear side or the front side? Do the manifolds still work?
In terms of the front of the rack, I don't see any concerns with the security door. I mean, I guess for your air-cooled components, you'd want to look at the impedance effect on that, right? On the exhaust side, there might be some challenges with the hose exhaust, so maybe you'd have to develop a custom one, maybe where it lets the hoses that go in and out of the rack get through the door, but still provide security. So there's some flexibility there, but we're not designing a security door specifically for liquid cooling. Mm-hmm.
So we know the connector has a 3 mm floating, right? So is that quick connect, the blind mat, there's a floating outlet built in there too?
Yeah, the valves are designed to float and rotate to take up some of the tolerances.
Got it. Thank you.
Any other questions? Okay, thank you.